In the context of software-defined radio usage for time and frequency transfer, let us investigate pseudo-random number generators and how they relate to global positioning system GPS data signal analysis. The outline of the presentation starts with introducing the spectrum spreading for complementing frequency transfer over a clean carrier by timing capability using spectrum spreading. Then the cross-correlation will be needed for fine time of flight recovery, and we'll try to lighten the burden of computing this complex quantity by reaching the Fourier domain and the relation between the cross-correlation and the Fourier transform. Because all GPS satellites are broadcasting on the same frequency, we need to identify on the ground where only the sum of all the electric field is detected which satellite has broadcast which message, and this will be achieved using code division modes to access. And finally, we will investigate some recording of a GPS signal to try to extract the various information relevant to the GPS broadcast. These records have been collected using one of these low-cost RTSDR DVB-T dongle, digital video broadcast receivers, fitted with an active antenna, the only additional element being a bias T to power the active antenna and separate the radio frequency component of the DC power supply reaching the active antenna. The concepts discussed in this presentation are not only applicable to global navigation satellite system GNSS, but also to noise radar, two-way satellite time frequency transfer, or even time transfer over optical fibers. So the impact of analyzing at the raw radio frequency level the GNSS information is that we can actually recover multiple physical quantities thanks to the high stability atomic clocks fitted in the satellite constellation, such as tide gauge by measuring the fine time of flight between the direct signal and the red reflected over a body of water, moisture detection by analyzing the reflected intensity, or actually one of the classical output of GNSS monitoring services is the total electoral content of the ionosphere. Many of these applications require the phase recovery, but we will see that actually the code already encodes multiple information that are useful from an educational purpose, where we actually identify each and every step of the GPS decoder. But even from a security perspective, analyzing the raw radio frequency data is the only way of detecting spoofing and mitigating spoofing and jamming by canceling the interfering source by null steering. So the radio frequency analysis using software-defined radio allows for recovering the genuine signal and cancel the jamming source. If a functional GNSS receiver is targeted, then the Barcelona-developed GNSS SDR is probably the best solution. Here we shall focus on the physical properties of the electromagnetic wave as collected by software-defined radio. The software-defined radio receiver needs not be a very complex one, since the L-band GNSS signals are broadcast between 1.2 and 1.6 GHz, well within the range of the DVB-T receivers are functional between 20 and 1.6 GHz. The poor resolution is not a hindrance because we will see that the GPS signal is below terminal noise, so that actually many receivers are single-bit comparator and the 8-bit resolution will be more than enough. Finally, the 2.4 MHz bandwidth will be sufficient for decoding the 1.023 megabit per second spreading over a 2 MHz bandwidth below the 2.4 MHz bandwidth of these USB receivers. When investigating GNSS signals using software-defined radio, the literature identifies Kaisbor's software-defined GPS and Galileo receiver as reference textbook, and in the beginning of the book we have an outline of the emitter chain. So starting from the 1023 MHz atomic clock, we see that an integer multiplication generates a carrier. If we do not focus on the military L2 band but only on the L1 civilian band, we see that 154 times multiplication of a carrier leads to the 1575.42 MHz carrier, which feeds the binary phase shifting BPSK modulator, meaning that the output of this modulator is 0 or pi depending on the bit state 0 or 1 to be broadcast. The bits are generated by the coarse average code generator, which is the gold code generator from the name of Mr. Gold, which is clocked at 1/10 of the atomic clock rate, or 1.23 megabit per second. This 1.23 megabit per second encodes a 1023-bit long code, and this code will repeat every millisecond. In addition to broadcasting the identifier of a satellite, the navigation messages, which include ephemeris, time offset of a clock, is encoded at a slow rate of 50 bits per second using an XOR of this code. XOR is selected because it's a one-to-one relation between input and output. If on the receiver side we receive the XOR message and we know what the code is, then because XORing with 0 is the identity and XORing with 1 is the opposite of the outgoing bit, then we can recover the navigation message on the receiver side. These bits are clocking the BPSK input with, on the other side, the carrier frequency, so that at the output with an IQ modulator, the L1 GPS band is broadcast. So now that we have the outline of all the items that need to be addressed, let us start with spectrum spreading. The pure carrier is a sine wave, and the sine wave has no timing information. All periods look similar to each other, and the Fourier transform of a sine wave is a unique spectral component at the frequency of a sine wave. There is very little information. If we want to introduce some sort of timing information, we might flip BPSK encode 1 out of 2 periods. By doing this, we can identify even periods or odd periods as encoded with 0 or pi phase. The timing capability is a bit better. We see some additional spectral component appearing in the spectrum, but not very efficient because only 1 out of 2 periods can be detected. If we generalize the concept by using a pseudo-random sequence or a non-repeating sequence of phase flipping, then we see that only when this sequence of phases is detected on the ground will the correlation detect the time of flight. In terms of spectrum, the spectrum has been spread as a continuous spectrum by this pseudo-random pattern of phase flipping, and this is closely related to Shannon's information theorem, where the spectrum bandwidth relates to the amount of information that can be transferred. Here we see that the spectrum has been spread by introducing this timing capability, and only by using this pseudo-random sequence of phase can we detect the time of flight. There is a close relation between the power spectral density and the autocorrelation, since one is the Fourier transform as the other. And if we look in the correlation function, we see that the autocorrelation of sine wave is a constant function. There is no timing capability in the sine wave. By flipping 1 out of 2 periods, we do have some sort of structure in the autocorrelation, but yet there is some uncertainty because the correlation will maximize periodically, and only by using the pseudo-random sequence do we actually achieve a unique Dirac function in the time domain, which is the time of flight. So these are implemented using GNU Radio for prototyping. However, GNU Radio will not provide the correlation block. So we need to relate the convolution and the correlation to the Fourier domain. Indeed, all these quantities are integrals over a number of samples, and if we replace the integral with a sum, we see that the correlation multiplies each signal sample with a pattern time shifted. The objective being to try to find at which tau time offset the pattern is detected in the noisy signal. The pattern detection is achieved by integrating the energy, and only if the pattern matches the signal position will the negative multiply with negative, positive multiply with negative, and energy will accumulate. Otherwise, the mean value quantities will average out and the integral will be a mean value 0. If we replace the integral with a sum in the discrete time, we see that we must sum the n elements of the code length, and this must be repeated for n possible offsets, so we have n calculation of n multiplications or an n squared complexity algorithm. If we wish to lower the computational burden, we can see the close relation between the correlation and the convolution, where here time is going backward, here time is going forward. And from the convolution theorem, we know that the Fourier transform of convolution is the product of the Fourier transforms. Thanks to the fast Fourier transform, this computation here is an n log n complexity rather than an n squared. The time reversal is achieved by considering the complex conjugate of the second argument, so that the correlation Fourier transform is the product of the Fourier transform of a signal times the complex conjugate in order to flip time in the second argument. So now that we have identified the structure of the calculation, let's see how to implement in GNU Radio. GNU Radio is a free open source framework for prototyping discrete time signal processing with multiple functionalities. By looking at the various blocks, we can actually search for the targeted function. And if, for example, we are looking for a noise source, with this signal will be our non-repeating pattern. We might want to check the quality of this noise source by displaying a spectrum, which is expressed as a queued frequency sink in GNU Radio, but linking this noise source to the virtual noise source to virtual sink will overload the CPU capability because GNU Radio has no knowledge of time flow. Here we have virtual source, virtual sink, so that GNU Radio has no way of clocking the data stream. We must introduce a block that slows down the data rate and focuses the scheduler to only generate the right number of samples per second, which is a throttle block. All quantities are reference to the sampling rate, since discrete time signal processing requires that we define the boundaries of a spectrum as minus half the sampling rate to plus half the sampling rate or the Nyquist frequency. Having defined this sequence, we can save this first flowchart as a first example and see how it executes by running the flowchart. Surely enough, the Fourier transform of noise is a flat spectrum. Middle button allows for tuning the parameters of the Fourier transform. So having identified the basics of GNU Radio, we might wonder what the blue icon here means. And if we have a look at the types of data that GNU Radio knows how to handle, we see that dark blue is a complex floating point number with imaginary part and real part. Naturally, software-defined radio will operate on complex numbers, since the baseband spectrum spanning from minus half a sampling rate to plus half a sampling rate has no reason for being even, and a non-even spectrum is represented by complex numbers. We will be handling real numbers, floating point numbers, which are orange, and we will see that 8-bit integer data are pink or purple colored. The implementation of a correlation through the Fourier transform involves coding the FFT block, and we might want to consider how the Fourier transform will be calculated. If we connect the output of the throttle block to a fast Fourier transform, the GNU Radio is complaining because calculating an integral requires a finite number of elements, and here GNU Radio is streaming continuously data. So we cannot directly connect the throttle block to the FFT, but we must convert a stream to vector so that the continuous stream of data is accumulated as a vector of the right length. Now here we still have an error because by default the stream to vector will not accumulate the right number of elements, and since this quantity will be reused multiple times in our flow graph, as common in programming, we will create a variable. If we have defined this variable n as the length of elements, we must define a variable here, which is a Python structure that assigns to the variable ID, the name, the quantity, here for example 2048, the number of elements we wish to process. Now, once we've performed the Fourier transform, the aim is to multiply conjugate and perform the inverse Fourier transform. Direct or inverse Fourier transforms are a matter of convention as long as the inverse of the Fourier transform remains identity, so that exponential of j omega t or minus j omega t might be considered as direct or inverse. So here, in order to center the zero time delay offset, we will first perform the reverse Fourier transform, multiply conjugate, and use the frequency sink as a direct Fourier transform at the end of the calculation. We can copy this block as the second data stream, since the first one will be the reference data, the second one will be the noisy data that has been recorded. And having done this, we can multiply conjugate the outcoming elements. So if we multiply and use the multiply conjugate block, again, GNU Radio will complain because the multiply conjugate operates on streams and not on vectors. So we must indicate that we're going to multiply n element vector. Finally, if we wish to display the outputs, we would like to connect the output of multiply conjugate with the frequency sink. However, the spectrum analyzer requires a stream and not a vector. So again, we do the opposite operation, where we go from a vector to a stream, operating on the n elements of the Fourier transform, and conclude by running the stream output to the frequency sink. Having done this, we can now execute the flowchart to observe that after middle button and autoscale, the cross correlation is maximized at 0 time offset. We now wish to make this simulation a bit more interactive by introducing a user tunable delay, and this user tunable delay will be introduced between the reference remains with 0 time offset and the time of flight is measured on the signal. Now, to make a simulation user interactive, we can define the delay as acute range, and if we inform this delay as an integer going from the FFT length, going from minus half the number of sample to plus half the number of sample, we can ask to have a range going from minus half the FFT length to half the FFT length. Because the delay must be an integer, we double slash to indicate it's a Python operation which outputs an integer quantity. This delay here will allow us to introduce the delay, and actually we can speed up a little bit the simulation by increasing the sampling rate to accumulate data more quickly in the Fourier transform. Now that we've completed this new flowchart, we can actually middle button autoscale and see how by moving the time delay, we indeed move the correlation peak, and the correlation peak is a fine estimate of the time delay. The correlation peak is 1 chip long, and the time resolution is given by the inverse of the bandwidth. We can see how performing the Fourier transform, multiply conjugate, and inverse Fourier transform indeed allows for computing this quantity. This is a very important topic if we look at the implementation of a cross correlation under GNU Octave. We shall see that its implementation heavily involves fast Fourier transforms. Indeed, when searching for FFT in the source code, we do see that the reference signal is FFT, the surveillance signal complex conjugate of the FFT, and the cross correlation is actually computed as the inverse Fourier transform of the product of these two quantities. So understanding practical implementation of the Fourier transform requires that this Fourier expression is understood for a reading cross correlation implementation. Furthermore, if we implement this for noise radar analysis, then we can benefit from the linearity of the fast Fourier transform. In this demonstration here, we have the same noise source throttled to make sure that we don't overload the processing capability of the CPU. But this time we have 3 delays. These 3 delays are driven by triangle shape, square shape, or cosine shape functions that will represent 3 possible targets. These delays are added because the receiving antenna of the radar system detects the sum of the reflector signals, but yet because the fast Fourier transform is linear, we will get 3 correlation peak by multiply conjugate with the reference signal. By taking the fast Fourier transform again in the time domain, we shall detect the various delays. Running this example indeed shows the 3 correlation peaks, and these 3 correlation peaks do represent the shape of the time delays introduced in the 3 targets, with the triangular wave, the sine wave, and the square wave representing the 3 sources of delays from the scene being illuminated by the radar system. This example is highlighted on this slide again. The pulse compression ratio is the indicator of the quality of the wave that has been selected for the time transfer. The pulse compression ratio is a trade-off between the fact that lowering the noise is achieved by running a sliding average, so that the longer the duration of the message, the better the averaging capability. However, the longer the code, the less timing capability we have because the energy has been spread over a longer duration. The objective is hence, rather than having a uniform window, to have some sort of structure so that the correlation of the beginning of the window does not correlate with the end of the window. As an example, a chirp will allow such a result because the beginning of the sine wave is not the same as the sine wave, a chirp being a varying frequency signal, sine-shaped signal. So that when we run such a window over noise, we do have the averaging capability. Indeed, the noise level has been decreased, but in the case of a uniform window, we see that the timing capability has been greatly decreased because all signs can correlate with the beginning signs can correlate with the end signs. On the other hand, if we do have this chirp, then the correlation only occurs when the chirp overlaps the pattern, and we see that only a single correlation peak results from such an analysis. In general, we can see that uniform window will have high averaging capability but no timing capability, and the broader the chirp, the better the timing capability. Here a 500 Hz chirp, here a 7 kHz chirp with a single correlation peak which is inverse of 7 kHz wide. Hence, B times T, the bandwidth of the waveform multiplied by the duration, is a unity-less quantity, the pulse compression ratio, that determines the signal-to-noise ratio improvement by correlating with the sine wave. In digital domain, the bandwidth is the data rate, the bits per second, and T, the duration of the message. If we multiply bits per second per duration of the message, we end up with n, the number of samples in the code. So the longer the code, the better the signal-to-noise ratio improvement, and the correlation peak width is solely given by the bandwidth or the maximum minus minimum frequency of a chirp in case of a sine wave. GPS could have achieved the same signal-to-noise ratio improvement by averaging over a long duration, but had it only used a sine wave, we see that the time capability would have been strongly degraded. By using a pseudo-random sequence to encode the information, as we have just seen, we do have timing capability with a single Dirac function at the center of the time of flight. So the sharing with the user on the ground the random sequence would be inconvenient had it not been determined by an equation or a reproducible strategy. Galois has invented the linear feedback shift register with maximum length, which means that if we have a register, binary register of n-bit length, we can encode in binary domain 2 to the n quantities. Actually, one quantity is forbidden because we see here that we are going to feedback as the input of linear feedback shift register the XORed values of two positions within the register to try to create this 2 to the n length sequence. And if we had all zeros, 0 XOR 0 will output 0 and the register would remain in the 0 state. So actually 0 is a forbidden state, and we end up having a length 2 to the n minus 1 sequence, non-repeating sequence, encoded by a register of n bit long. Now, the question is, where shall we locate the tap positions? Where shall we locate the input of the XOR so that if at each clock cycle, the content of the shift register is shifted to the right, the last bit is dropped as the output of the linear feedback shift register, under what condition is the tap location leading to a maximum length sequence, meaning a 2 to the n minus 1 long sequence. The algebra theory developed by Galois is non-trivial, but we do find on the internet at Carnegie Mellon University the webpage of Professor Koopman, which describes all the maximum length linear feedback shift register tap locations as a function of register length. If we look over here, we have selected a 7-bit long linear feedback shift register, so that we see in the entry over here that quite a few tap locations will lead to maximum length sequences. Maximum length meaning that the pattern cannot repeat, as 2 to the n-1 will go through all possible variations of the content of this register. Let us remember, for example, that register tap locations 41, this is hexadecimal, we see here hexadecimal, 41, 48, or 60 are possible maximum length tap locations. If we look at the scheme that was described on the slide, we see here that, for example, we go from the least significant bit to the most significant bit, so that we have 1, 2, 4, 8, and 1, 2, 4, this is represented as hexadecimal 48. We see here 1, 2, 4, 8, 1, 2, 4, this is 2 plus 4, this is 0x60. Indeed, these two tap locations, 0x60 and 0x48, are indicated as maximum length sequences. These sequences can be very easily assembled using a couple of integrated chips, linear feedback shift register, linear register, and the XOR, or can be implemented quite efficiently in field programmable gate arrays, FPGA, or software-defined radio. However, here we wish to address, using GNU Radio, how we can observe the orthogonality of pseudo-random sequences and pseudo-random generators. So starting from our previous example, rather than using a noise source which is difficult to share with the users on the ground segment, we will have a reproducible way of generating random non-repeating sequences with an easy way of sharing with the ground segment the definition of these sequences. The Galois linear feedback shift register does provide such a capability in GNU Radio, with the output being a floating point number, which is not compatible with the complex quantity that has been involved earlier. However, since the Fourier transform multiplied by complex argument the input floating point number, the final elements of the flowchart will remain complex quantities. We wish to demonstrate the orthogonality of codes, and the block here is configured with the degree, or the linear feedback shift register length, and the mask being the tap location of these XOR gates. So now we see again that we have put the same sequence in both arms, so that the output is a set of correlation peaks. Now, for a 7-bit long sequence, 2 to the 7 minus 1 is 127, and actually the correlation peak repeats every 127 samples. Since we have performed the Fourier transform on 2048, we do have 2048 divided by 127 correlation peak that will appear in the cross correlation. If, on the other hand, we select a different maximum length sequence, this time the correlation peak will be inexistent because the energy will not accumulate. Hence, if we run the sequence representing the gold code of the appropriate satellite, we will get correlation peaks repeated every sequence length, 1 millisecond in the case of GPS. If we encode on the ground a sequence that is representative of a satellite that is not broadcasting, then we will get no energy in the correlation. We thus have the means of spreading the spectrum in a reproducible way and easily described in an algorithm through the Galois linear feedback shift register, only requiring the location of the taps and the register length. As can be seen, the spectrum of the GLFSR of maximum length is flat, since there is no repeating pattern. And again, if we correlate with the right pattern, we do get correlation peaks every 120 samples, and no correlation if we run the code through the wrong sequence. This can actually also run on analog signal processing, such as the fast Fourier transform analyzer from Hewlett-Packard, which allows on both channels to analyze the spectrum spreading capability of the pseudo-random sequence, and by exactly taking the multiplication we've seen, calculating the time delay between correlations. So now that we are convinced that we understand how spreading the spectrum allows for time recovery, we need to understand the various steps for decoding GPS. The challenge of decoding the GPS signal is that it encodes the information over the phase, which requires fine phase recovery. Indeed, if the phase encodes as 0 and pi the bit state that is being transmitted, then any phase rotation due to frequency offset between transmitter and receiver will add some continuously evolving phase component 2 pi delta ft when frequency delta f is introduced between transmitter and receiver. So this frequency offset must be compensated for in order to avoid any rotation of the phase and allow for easily detecting the state of the phase so that we can recover the bit that was encoded. The trick for NPSK, which is the n-stage representation of phase shift keying, is that the nth power of the signal, where the delta omega t, which is 2 pi delta ft, 2 pi the frequency offset between transmitter and receiver, is added to the random phase that we wish to detect. This phase here in NPSK is 2 pi to the n. In the case of BPSK, binary phase shift keying, this phase will take two possible values, 0 or pi. If we now raise this quantity to the nth power, we include the n inside the argument of the exponential, and we end up having n phi being always 2 pi. In the case of BPSK, 2 times phi is 2 times 0 or pi, which is 0 or 2 pi. So that the output of taking the nth power of an NPSK modulated signal is a clean carrier, and this clean carrier will be at n times the frequency offset. If we know n times the frequency offset, then we can subtract the division by n of the frequency of a clean carrier and recover the initial phase information with no unwanted phase rotation. This is true for BPSK. This will also be valid for QPSK, as for example used by the Meteor M2 Russian weather satellite, where the raw signal is obviously spectrum spread, the squared signal remains spectrum spread, but the fourth power of the signal exhibits a single carrier which is 4 times the frequency offset. This processing scheme is demonstrated in the following GNU Radio flowchart, where the objective is to allow for recovering the phase quantity that encodes the bit state and get rid of the frequency offset. Let us analyze now this example. We see here that we start with a signal that is to be transmitted, a square wave of amplitude 2 offset -1, so that it will be valued +1 or -1. And if we multiply the carrier frequency with this square wave, which represents the bit states, then we shall have a BPSK modulated either 0 phase, which is +1, or pi phase, which is -1. We add some noise, and the Costas loop is the block that will perform the operation we discussed, namely cancelling the phase, spectrum spreading, phase modulation, and recovering the carrier to cancel any frequency offset. The documentation tells us how the loop order should be 2 pi over 100, and the modulation order is 2 for BPSK, 4 for QPSK, or 8 for APSK. Hopefully, if the Costas loop operates properly, the recovered phase should be the encoded message. And prior to Costas loop, we will see that the signal will suffer from phase rotation, making the identification difficult. Finally, squaring the signal acts similarly to the Costas loop by cancelling the phase modulation. What we see here now is that prior to the Costas loop, the blue curve is rotating. The Costas loop has cancelled the spectrum spreading by the phase modulation to recover the to cancel the frequency offset in the red, which indeed looks very similar to the green curve. This is true whether we change the frequency offset that is introduced to carry the phase, until the Costas loop will collapse and lose its tracking ability, adding now the phase rotation to the bit state, when twice the frequency is reaching the sampling rate. Indeed, the spectrum spread phase modulation still fits well within the allocated bandwidth, but if the double frequency offset reaches close to the sampling frequency, then the signal-to-noise ratio will degrade and Costas loop will no longer able to detect and cancel the frequency offset. So indeed, now the challenge is that for NPSK, n times delta f must remain much smaller than half the sampling rate. The Costas loop is a core element of any phase-modulated signal analysis, as it is mandatory for cancelling the frequency offset between receiver and emitter. Even if we were to have atomic clocks on our receivers, the motion of the GPS satellite along its orbit will necessarily introduce some sort of frequency offset between the receiver and the transmitter. Having now analyze all the various elements needed to decode the message of the GPS, namely the spectrum spreading, the Costas loop for cancelling the phase offset, and the various signal processing tricks for recovering the information. Let us investigate real data. Now, a data set has been stored on the IQ Engine website. IQ Engine is a repository where IQ datasets are stored under the GNU Radio. We can check what kind of data are available, especially under the space segment. And under space, we shall find the dataset of GPS L1 record, including not only the data, which are rather large files, but also the meta information which will describe the content of the file. The SIGMF meta file informs on the data format, it's 8-bit integer data, interleaves I and Q quantities, and the sampling rate is 1.23 megabit per second. The carrier frequency has been removed by the software-defined radio receiver, but is still documented in the header. So we shall collect this data file and observe its content. The structure of the signal will be investigated using the file source signal. So if we go for file and we consider that we wish to read the content of this file and we select the data file SIGMF data, which is the 640 megabyte file, and we inform that it is a byte format, then we are ready to run the content. We have seen that the data rate is 1.23 megabit per second, and we can try to display the output on a frequency sink. However, the output as interleaved integer character must be converted to floating point numbers by using the iCar2 complex, and the documentation informs that the scaling factor is actually inverse scaling factor must be 127, so that the plus or minus 127 range of the characters are scaled to the plus or minus 1 expected by GNU Radio. Again, because there is no hardware clock in this system, we must throttle so that we can display properly. We can try to find and analyze the FFT, and by saving these flowcharts, we will be ready to execute and observe that FFT of a GPS signal does not exhibit any structure. We are unable to detect which satellite is broadcasting. The analysis of a link budget indeed demonstrates that GPS is below terminal noise by considering the Freeze equation, where the energy broadcast by the satellite decays as d squared, because energy conservation spreads the energy over the sphere of area 4 pi d squared, and this sphere over which energy is spread intersects the receiver antenna of typical dimension lambda squared. Then the amount of energy recovered on the ground is the ratio of the received energy to the emitted energy, is lambda squared, the area of intersection with the sphere over which energy is spreading, 4 pi d squared, and this area is normalized to the 4 pi steradian area of the sphere surrounding the receiving antenna. The GPS satellite is not emitting over the whole isotropic volume, but towards the Earth, and the antenna exhibits 13 dB versus isotropic antenna gain, and this gain, G1 and G2 for the receiving antenna, are added in front of the link budget. Freeze equation states that energy conservation is met if received power to emitted power is antenna gain times lambda squared divided by 4 pi d squared. In other words, by taking a logarithmic scale, the free space propagation loss of 10 log of this quantity here will tell us that the losses during the propagation is 20 log of f, since the wavelength lambda has been converted to a frequency lambda equals c over f, plus 20 log of distance, 20 because 10 log of d squared becomes 20 log of d, and 147.55 constant is actually 20 log of the speed of light c that was used to convert wavelength into frequency over 4 pi. Now, by doing the analysis, we are informed that GPS transmits 50 watt or 7 dB watt, which is converted in 50,000 milliwatt or 47 dBm on a carrier frequency f that will feed the free space propagation loss over the wavelength variation over here, with a 13 dBi coming over here. So the 20,000 kilometer, which must be converted to meter, is this quantity here, so that we find that the free space propagation loss is 182 dB with respect to the 47 dBm plus 13 dBi, or 60 dBm on the ground, so that we have 60 minus 182 ends up being minus 122 dBm received power. This result is consistent with regulations of GPS that states that on the ground a minimum power of minus 130 dBm must be received. However, over the 2 MHz bandwidth, the noise thermal density at room temperature at 300 K is the Boltzmann constant multiplied by the temperature in Kelvin, and this is minus 174 dBm per hertz. Multiplied by the bandwidth of 2 MHz or 63 dB, we end up having minus 174 dBm per hertz plus 63 dB, which is the bandwidth of a GPS signal, or minus 111 dBm. We hence see that GPS minus 122 is 10 dB below the terminal noise of minus 111 dBm. So, hence, the GPS signal cannot be detected on a spectrum analyzer other than a slight disturbance over the noise, the spectrum of the noise. However, we have seen that the spectrum spreading can be cancelled by squaring, and the d-spreading will lead to, for energy conservation, the d-spreading will lead to the accumulation of energy by a signal-to-noise ratio improvement equal to the number of bits, namely, in the case of a 1000-bit long sequence, 30 dB. So if we now multiply the signal and actually use a second channel of the Fourier transform analysis to observe prior and after multiplication, we shall see now, by using some averaging, that on the first channel, which is the square signal, we now have these additional peaks which are not visible on the bare signal, and all these signals are actually energy broadcast by each satellite at double their frequency offset. Hence, squaring the signal can bring the GPS above the terminal noise. If this squaring procedure is repeated over multiple measurements, here spanning multiple hours, the tracks of the satellite as a function of time, y-axis is the Doppler shift, x-axis is time, is visible. Indeed, GPS satellites with their period of 12 hours will rise over the horizon, fly overhead and set on the opposite side of the horizon, following a typical arctangent function of their velocity distribution. As was mentioned earlier, the Codeless technique degrades the signal-to-noise ratio with respect to correlation because the noise itself is squared as well, so that the real decoding of a GPS signal will involve a correlation using the processing technique seen earlier. So we now have all the information for decoding GPS signals by not using squaring codeless processing but by using correlation, and each one of the satellites is identified by a unique code, more complex than the Galois linear feedback shift register seen earlier, since the gold code is made of two interleaved linear feedback shift register outputs. The ultra-stable clocks, hydrogen maser, rubidium clocks on board the GPS will provide the high stability, but nevertheless, the motion of the satellite will require that we compensate for the Doppler shift. We aim at computing the time of flight and identifying the different time of flights called pseudo-range, locate the user on the surface of the Earth as the intersection of four spheres, four because the free quantities of space and the time offset between the ground clock and space GPS time must be identified. Before investigating the full decoding using the correlation with a known code, we can actually check whether a GPS signal was collected without relying on squaring, which increases the noise level by squaring the noise level. And as was discussed earlier, the GPS code repeats every millisecond because running at 1.23 megabit per second, a 1023-bit long code will repeat the code periodically. If we now look at the expression of a cross-correlation of a time delay code, we see that the autocorrelation, which is the signal multiplied by the time delay copy of the signal, as the signal is plagued by the 2 pi delta FT, the frequency offset between the emitting frequency and the down-based frequency, we do have this frequency offset. However, if we take the autocorrelation, which multiplies the signal by its complex conjugate, we see that the term delta omega t over here and over here will cancel, and we shall be only left with the term delta omega tau, and this delta omega tau is independent of the time over which the integration is calculated, so that this quantity can come out of the integral. The integral of exponential j phi multiply exponential by minus j phi t plus tau is actually the autocorrelation of the phase, and the phase being the pseudo-random sequence of the gold code will end up being the correlation peak of the pseudo-random sequence. If we expand our previous flowchart with the modification for implementing this algorithm, we have file source converted to a complex quantity. Prior to this analysis, we did the squaring, and now we can actually have the autocorrelation by taking a Fourier transform, multiply conjugate, and inverse Fourier transform to display on the time sink the time evolution. And again, in this demonstration, we will see that the raw data does not exhibit any structure on the spectrum of a GPS signal. Squaring the signal does allow for identifying the various satellites, and this time we have included a low-pass filter to zoom in the central aspect of the spectrum by getting rid of the outer parts of the spectrum which do not include any relevant information. And by looking at the autocorrelation, we see here the peaks that repeat once every millisecond. So we have 8,000, 9,000, 10,000. So every millisecond, the cross-correlation, the autocorrelation peak repeats. So this demonstrates various techniques for detecting spread spectrum information, either by taking the nth power of NPSK or by autocorrelating as long as the code repeats periodically. We now conclude by correlating with the code sequence of the gold codes. However, a remaining challenge is that by correlating a frequency offset signal, we are unable to accumulate energy since the mean value of a sine wave is 0, and if some frequency shift remains, then the correlation with the gold code sequence will not accumulate energy. However, prior to the gold code correlation, the signal is below terminal noise and the Costas loop is unable to compensate for the frequency offset. So we now have a chicken and egg issue because we need to compensate for the frequency offset to accumulate energy of the pseudo-random sequence, but the pseudo-random sequence energy can only accumulate if the offset is compensated for. This will lead to a brute force approach where both frequency offsets and code must all be tested. There are 32 possible gold codes up to 32 possible satellites in space. So we must know what are the frequency offsets that we must consider to compensate for the GPS Doppler shift. Furthermore, let us mention that thanks to the linearity of the cross-correlation, even though we are modulating on the phase, because the cross-correlation is a linear operation, then calculating the magnitude of a correlation allows for detecting which satellite is broadcasting with which time delay, as demonstrated in the simulation. But most importantly, if we add some phase offsets to the signal because the broadcast information is BPSK modulated, then this constant phase, which is not time dependent, will come out of the integral and will affect the cross-correlation in the same way as it affects the signal. Indeed, we will be able to recover the phase that was broadcast on the correlation phase on the receiver side. So we end up having this scheme where the 20 millisecond navigation message, which is the 50 bit per second bit length, includes 20 copies of a correlation peak of the gold code, and this code can only accumulate energy if the local oscillator has been compensated for. So what are the ranges of frequency that must be compensated for? Some basic trigonometric search on the geometry of a satellite motion indicates that from Kepler's law, t squared over radius to the third power with respect to the center of the Earth of the orbit is a constant, so that a satellite flying at 20,000 kilometers altitude will actually perform a full orbit in 12 hours. Considering we know the length of the orbit and the period of 12 hours, we end up having the tangential velocity of 3.8 kilometers per second. However, the projection of the velocity towards the receiver involves a trigonometric analysis where the receiver is assumed to be on the surface of the Earth and the satellite is distance from the center of the Earth equal to the radius plus its altitude, so that we get the angle of the projection. And the actual angle of the projection is the sine is radius of the Earth divided by the sum of the altitude of the satellite plus the radius of the Earth. And because the projection over here will be the same sine angle, we end up having a projection which is the tangential velocity times the radius of the Earth divided by the altitude of the satellite plus the radius of the Earth. And this results for a carrier frequency of 1.57 GHz to a velocity leading to a Doppler shift of plus or minus 5 kHz. This would be an ideal condition had the ground clock been an atomic clock with perfect behavior. However, the practical clock we have on the ground are clocked by temperature controlled crystal oscillator TCXO, which in themselves introduce some large bias. So these are the plots of the Doppler shift as recorded by a commercial GPS or by using GNSS SDR as a software-defined radio receiver determining the frequency offset. But the local oscillator itself will add a significant contribution if we are not careful. We have introduced the target of using DVB-T receivers, and the low-cost DVB-T receiver exhibits frequency offset up to 100 ppm. 100 ppm at 1.5 gigahertz will be 150 kilohertz, meaning that we must greatly extend the frequency range that we investigate during the brute force analysis of the various frequency offset. This is a measurement at 100 megahertz of the frequency offset between a hydrogen maser and the DVB-T receiver, exhibiting the 75 ppm offset that is observed. So we must perform over a broad range of frequencies. What is the frequency step? The frequency step is determined by the duration of the message. The message is 1 millisecond long, so that we must accumulate energy over this 1 millisecond. If we want the phase rotation to be negligible over 1 millisecond, we must identify the frequency with better than 1 kilohertz. It is reasonable to try to search frequency steps of a few hundred hertz to minimize the computational load and yet allow for the energy to accumulate without spreading the information if the carrier frequency has not been properly compensated for. Furthermore, the data rate must be adjusted to tune to the downlink data rate. Indeed, by offsetting significantly the frequency range at which the chips are run, we see that again the correlation is degraded because the energy will no longer accumulate. So having discussed these principles, can now extend our flowchart with this latest analysis where we actually include the copies of the codes that have been used to encode the GPS space vehicle identifier, the gold code. So we again have our file source, which is converted to floating point numbers, analysis of a spectrum, the square signal. We autocorrelate the signal, but now we must, in addition, provide a frequency transposition, frequency offset, that represents the Doppler shift compensation. This Doppler shifted signal, so frequency offset, the frequency translating Fourier filter will offset by a center frequency, and the center frequency is user programmable. This DF is a slider range over here. And what we will be doing is correlating this frequency transpose signal with two possible copies of pseudo-random sequences. These are also uploaded in the SIGEF data on iqengine.org. We encoded pseudo-random sequence number 9 and pseudo-random sequence number 23 as defined by the gold codes. We stream to vector, take the Fourier transform, multiply, conjugate, and inverse Fourier transform to perform the correlation, and we display the time domain plots of correlations. Running this flowchart, we see again the spectra and the spectra of the square signal, the autocorrelation, and this time we have tuned the frequency offset so that space vehicle number 9 is accumulated. If we search a little bit around the frequency, we can actually search for the frequency of the second space vehicle that is visible over here. So what we do see is that by searching the various frequency offsets of the various codes of the satellites that are visible, we will be able to identify which satellite has been flying overhead during the record. If we convert this space vehicle number 23 with space vehicle number 10, we might search for the frequency offset that will allow detecting the signal, but if space vehicle number 10 has not been recorded, the correlation will never accumulate. And indeed, on the top chart, whatever the frequency offset that we search for, we are unable to detect the signal, whereas the second chart from top will exhibit the correlation when the frequency is compensated for. So this summarizes the complete steps needed for acquisition of the GPS signal. In the acquisition phase, we run through all possible pseudo-random sequences, and we run through all possible frequencies with a few hundred hertz steps and a range of plus or minus 5 kilohertz around the frequency offsets introduced by the software-defined radio receiver. Indeed, for multiple low-cost DVB-T receivers, we find frequency offsets up to plus 60 ppm or minus 70 ppm, meaning that we must greatly expand the frequency range that we must search the frequency offset to compensate for the Doppler shift and the frequency introduced by the receiver. In this analysis, we can check actually that the space vehicles identified by this processing are the same as the one by the U-Center software of commercial U-Blocks receivers. In this experiment, the signal from the GPS antenna was split between the software-defined radio and the U-Blocks, and indeed we can identify G meaning GPS, R is Russian GLONASS, E is European Galileo, so G31, G11, and G14, which are the various receiver signal S found on the SDR plot, where the color indicates the cross-correlation maximum. The strongest signal of GPS match the received signal on the SDR. Now, once the brute force acquisition has been completed, then we can shift to a tracking mode where, knowing the satellite position in space, indeed the Doppler shift and its identifier, there is no need for searching for all possible solutions, but only a delay locked loop and a phase locked loop tracking the frequency will be enough to identify the fine changes of the frequency and the delay offset in the sampling of the data, and we record then the navigation messages that feed the position, velocity, and time solver, the PVT solver. This requires that we can, on the one hand, detect with pi phase rotation uncertainty the course phase to track the DLL and PLL, and then that we can actually recover the navigation message as 0 or pi, and this is achieved by comparing arctangent of Q over I with respect to arctangent 2 of Q and I. Arctangent Q over I is pi insensitive because -1 and -1 will give the same result as 1, 1 for Q and I, whereas arctangent 2 remember the individual sign of I and Q and can have 2 pi uncertainty, hence recovering the navigation message. This concludes our investigation of the GPS signals, and we will conclude with a short experiment tabletop to demonstrate time transfer using pseudo-random sequence generators. In this demonstration aimed at showing how we implement two-way satellite time and frequency transfer using spectrum spreading, we wish to assess the time delay for between two channels of SDR receiver, and indeed we demonstrate how using only a 5 MHz bandwidth as allocated by the Telstar satellite propagating the two-way satellite time and frequency transfer for intercontinental time and frequency comparison, the 200 nanosecond sampling period is greatly improved on this tabletop experiment with perfect scale to node ratio, where we can actually measure time delay introduced by these spacers, SMA spacers 1 centimeter long, 1 centimeter at 20 centimeter per nanosecond is a 50-second pico delay, and indeed by introducing these spacers we do see 50 picosecond delay with sub-picosecond standard deviation. How is this experiment achieved? Here is a demonstration realized with my colleague Gwenel, where an FPGA is running a pseudo-random sequence and feeding this bandpass filter, since the FPGA runs on a GPIO, the BPSK modulated carrier at 70 MHz. The signal feeds a B210 software-defined radio receiver, and the clock reaching the FPGA is coming from an octoclock, which is a 10 MHz output and a 1 PPS generator. The PPS is defining time, the 10 MHz is defining frequency, and because the FPGA needs a square wave, the sine wave is actually converting a square wave using this fast comparator. The B210 software-defined radio receiver can either be clocked by the same 10 MHz or by its own internal TCXO. So let's see how we're going to use this hardware for demonstration of time transfer. So here we have the software-defined radio source, which is a B210 SDR, and because there is a hardware clock driving the flowchart, there is no need for a throttle block this time. We're going to look at the time output of the B210 signal in the frequency domain. We compensate for the frequency offset between the transmitter and the receiver, and we perform a correlation by going into the Fourier domain and inverse Fourier transform to display the various quantities of interest. The correlation is calculated with respect to a local file that holds the pseudo-random code that is implemented in the FPGA for spreading the spectrum. If we now first start with an external clock on the B210, we see that the phase is flat, so meaning that there is no frequency difference between the two generators, and the correlation peak, which is the output of the inverse Fourier transform, is static, is not moving. If, on the other hand, we use the internal clock of the B210, meaning that the FPGA is run by one clock source and the B210 with another clock source, this time we will see that the phase exhibits a slope. The slope is the frequency offset between the transmitter and receiver. We see also this variation of the frequency as the beat node between I and Q coefficients. On the bottom is the 70 MHz intermediate frequency spectrum matching the requirements of the Telstar satellite. And most importantly, we do see that the correlation peak is moving as representative of the frequency offset between the two speakers. Most importantly is the fact that this frequency offset is only detected on the code correlation and not on the carrier. Why is this important? Because if we now switch back to the same clock source, we know in a two-way satellite time and frequency link that both ends are perfect, National Meteorological Institute, but the frequency offset introduced by the satellite is unknown. However, if we were to analyze the carrier frequency, then we would be impacted by the satellite, which is not part of the meteorological link. Here we are introducing on the carrier frequency an offset df, and this offset df is the one we can tune over here. What we do see is that the correlation peak is static since both ends are clocked by the same frequency source, but even adding a frequency offset does not impact the code delay that represents the frequency difference between emitter and receiver. So the fact that we are using only the code analysis to detect the frequency makes us insensitive to any carrier frequency offset introduced by the satellite. This concludes this introduction to the usage of software-defined radio for time and frequency transfer. Thank you for your attention.